Okay, so let's solve some problems about the first law of thermodynamics. The first one is an isothermal expansion. 1 mole sample of an ideal gas. So we have an ideal gas. It's 1 mole, so N is equal to 1. And we have an ideal gas, so PV is equal to nRT. Is kept at 0 degrees Celsius. Temperature is 0 degrees Celsius, which is roughly 273 Kelvin, and it is expanding from an initial volume of 3 liters, which is 3 times 10 to minus 3 meter cube, to a final volume of 10 liters, which is 10 times 10 to minus 3 meter cube, and it's done at a constant temperature kept at 0 degrees Celsius. Therefore, I should note that this is an isothermal expansion process. So let's look at part A of the problem. How much work is done on the gas during the expansion? Since I have PV is equal to nRT, pressure times volume is a constant, it's 1 mole. The universal gas constant is 8.312 joules per mole Kelvin, and the temperature is 273 Kelvin. So pressure times volume must be equal to this number. And therefore, the pressure changes as a function of volume. 8.312 times 273 divided by the volume, and this volume must be in meter cube. And I find that the work done in this process is minus V initial to V final integral P dV. So this will be minus the integral 8.312 times 273 divided by V dV from V initial, which is 3 liters, V final is 10 liters. So I can calculate the total work done on the gas. It's going to be 8.312 times 273 natural logarithm. Because of the minus sign, the limits will change. 10 times 10 to minus 3 meter cube divided by 10 to minus 3 meter cube, and I find the answer to be, the total work done is minus 2.7 times 10 to 3 joules. Now it's important to do a sanity check here. I got a negative answer. The final volume is greater than the initial volume, so the gas has expanded. Gas has done work on the environment. The environment has done negative work on the gas. So that's how we should interpret it. In part B, how much energy transfer occurs by heat between the gas and its surroundings in this process? Now, in an isothermal process where the temperature is kept constant, we have the internal energy change is 0. We're basically changing, we have a state variable. Internal energy has not changed because the temperature has been kept constant. We have Q plus W is equal to 0. Therefore, the heat added to the gas is minus the work done on the gas. So this will be equal to 2.7 times 10 to 3 joules. That's the total amount of heat added, or the mechanical equivalent of this. So that would be the heat added expressed in joules. And now in part C of the problem, if you want to convert this to calories, remember 1 calorie is 4.186 joules. So how many calories of heat? If the gas is returned to its original volume by means of an isobaric process, how much work is done on the gas? Now the process has changed. I have an isobaric process. For the isobaric process, the work done on the system is equal to minus pressure times delta V. So the pressure at which I'm doing the process, it's the final pressure that is minus nRT divided by the volume at which I have started the process. It's the reverse process, so this has started at the volume 10 liters, so it's 10 times 10 to minus 3 meter cube. And the change in the volume is now from 10 liters to 3 liters. So this will be 3 minus 10, 10 to minus 3. So these 10 to minus 3's will cancel. So I will have as an answer, for the temperature I substitute 273. For R I have 8.312. N is equal to 1. So the answer will be 1.6. It's going to be plus 1.6, 10 to 3 joules. The work done is now positive because this is an isobaric process. It's also a compression. If it's a compression, that means there is positive work done because the volume is decreasing on the gas. The work done on the gas must be positive. Now let's take a look at another example. Suppose 1 gram of water vaporizes isobarically at atmospheric pressure. Its volume in the liquid state is 1 centimeter cube, in the vapor state is 1671 centimeter cube. Find the work done in the expansion and change in internal energy of the system. So I have 1 gram of water. The process is isobaric, pressure is kept constant, 1 atmosphere, 1.013, 10 to 5 pascals. That's actually 1 atmosphere pressure. Its volume changes from initial volume 1 centimeter cube to final volume 1671 centimeter cube. So how much is the work done in an isobaric process? So let me write here, this is an isobaric expansion process. The volume, final volume is greater than the initial volume. So I find that the work done must be equal to minus P delta V. So this should be minus 1.013 10 to 5. The final volume is 1671. The initial volume is 1 centimeter cube converted to meter cube is going to be 10 to minus 6. That's the conversion factor to meter cube. So I find that the total work done is minus 169 joules. That's the work done on the gas. And again, this work done on the gas is negative because the gas is doing the work by expanding. How much is the heat added to the system during this process? Well, this is a phase change process. There is phase change involved, and therefore I have the heat added to the system is latent heat of vaporization times the mass that goes through the phase change. And here I have this should be joules per, not degrees Celsius, it should be joules per kilograms. So this is going to be 2.26 times 10 to 6 joules per kilograms times the mass expressed in kilograms, 1 gram, 1 times 10 to minus 3 kilograms. So I find 2260 joules. And therefore, what it is asking me is the change in internal energy of the system. It's the heat added to the system plus the work done on the system. 2260 minus 169, it will be 2.09 kilojoules, the total internal energy change. Okay, so one more example. A 1 kilogram bar of copper is heated at atmospheric pressure so that its temperature increases at atmospheric pressure, so it's isobaric process. The temperature increases from 20 C to 50 C. So let's write here, it's 1 kilogram copper. Pressure is kept constant, 1.01 10 to 5 pascals, that's 1 atmosphere pressure. Initial temperature is 20 degrees C, final temperature is 50 degrees C. As a result of this, what will happen? There will be thermal expansion, so the volume of the copper will change. So we have the final volume of the copper will be beta times initial volume the change in the volume of the copper will be beta times the initial volume times delta T, where beta is the average coefficient of volume expansion, and remember this is approximately 3 times the coefficient of linear expansion. So this will be basically 3 times 1.7 10 to minus 5 per degree Celsius for beta. And the change in temperature is T final minus T initial, 30 degrees Celsius. And the work done for an isobaric process, this is an isobaric process where the temperature is changing, the volume will increase. The work done is equal to minus P delta V. So I will have here minus 1.01 10 to 5 pascals times delta V, which is 3 alpha, 3 times 1.7 10 to minus 5. Initial volume I have to calculate. I know its mass, I know its density. So the initial volume will be rho is mass divided by volume. So volume is mass divided by density of copper. So this will be 1 kilogram divided by the density of copper, 8.92 times 10 to 3 kilograms per meter cube. That's the initial volume. Times delta T, it is T final minus T initial, 30 degrees Celsius. And this has to be kept in degrees Celsius because of the unit here for alpha. So I find that the work done here is going to be minus 1.7 times 10 to minus 2 joules. It's negative because it's expansion. It's actually a thermal expansion going on. Copper is doing work on its environment. So that's the answer to part A. Part B, how much energy is transferred to the copper bar by heat? Well, there is no phase change here, so the heat added is equal to mc delta T. The mass of copper is 1 kilograms. The specific heat of copper is 387 per kilogram per degree Celsius. The change in temperature is from 20 to 50, 30. So this will be 1.2 times 10 to 4 joules of heat added to copper. And in part C, what is the increase in the internal energy of the copper? Well, that's the first law of thermodynamics. Change in internal energy is heat added plus the work done on the copper. So this will be equal to 1.2 times 10 to 4 minus 1.7 times 10 to minus 2. So it will be roughly equal to 1.2 times 10 to 4 joules. Basically, the work done on the copper or by the copper is negligible. And why is that? Because of this coefficient of expansion is becoming so small, 10 to minus 5, of the order of 10 to minus 5 for the copper.